Now that my wife has showed up, I think we can get started. I appreciate your coming out tonight. I know some of you were here last time, and I'm very glad that I didn't chase you away. I do want to be perfectly honest with you that this talk on physics tonight is likely to lack some of the drama and raw emotion of the Senate hearings today. And I also want to say that, just to set the record straight, that this is not going to be an assault on physics, and I have always had the greatest respect for physics. So what I wanted to do to start tonight is to go back and talk a little bit about some of the things we talked about last week, sort of a summary for those who weren't here, and a reminder for those who were. The goal of this course is to understand what science has to tell us about the world, but also to understand its limitations. Ultimately, the question that I'm trying to answer is there space for God in our understanding of all that is? And I hope to show that science is unable to provide a complete explanation. One of the key elements that underlies this series of talks, one of the key assumptions is that there is one truth. There is one objective reality. It may include things that are seen and unseen. But whether we know what it is or not, there is one truth out there, and we have an opportunity to try to figure out what it is. It may include God. It may not include God. It may include one universe. It may include many universes. But there is an objective reality, and it is intelligible to us, at least at some level. And I also believe that how we resolve those questions, what decisions we make, should affect the way that we live our lives. I also believe that science is an important way to understand much of this reality. It is based on observation and experimentation, which is its great power, but it's also its greatest limitation. And we'll talk a lot about that during these talks. There are things that are simply beyond the scope of the inquiry of science. I'll seek to demonstrate what some of those limitations are. And what I want you to understand is where science cannot provide an answer, there is an explanation. Science can't provide it. Something else is going to have to fill that gap if we want to understand all there is. The other thing that we talked about last week was knowledge. How we acquire it, how we process it, and some of the issues with reliability of knowledge. We gain most of our information about the external world through our senses. But there is also an internal world that we have, which is where all of our subjective experience of those senses are. But there are also our emotions, love, our deep sense of morality, which is very common throughout the world. And both of the external world and the internal world we make sense of through reason. But reason is also capable of providing its own truths, such as mathematical or philosophical truths. But there are problems with our understanding of the data that we get and the information. And this really has to do with our cognitive structure that we cannot set aside. As I mentioned last week, John Polkinghorne calls this the spectacles behind our eyes. And there are really two aspects of this. One is nature. There's both nature and nurture. And in terms of nature, each of us is built slightly differently. And we actually see the world and smell the world and taste the world somewhat differently. There's also nurture, which is our experience of the world, our personalities, the experiences that we have, the associations we have with different stimuli. And that affects how we perceive the world, but it also affects how we interact with the world. So some of the conclusions that we came to last week are that human beings are processors of information who are all calibrated differently, and our experiences in and of the world are different and unique. This applies to scientists as well. What we know or believe is imperfect and incomplete, and all we think we know, including scientific knowledge, is in fact a form of belief. So that's a summary from last week, and now we're going to talk about physics, and I'll bet not many of you thought you'd be sitting around listening to physics for 45 minutes. But here you are. So I want to start with some of the basics, and I want to start with fundamentals about what we know about reality. And first, there is one major question that has plagued mankind since we've been around, and that is, why is there something rather than nothing? And there's a corollary to that, which is, how is there something rather than nothing? And the reality is that science really can't speak to this issue. Now, that doesn't mean science doesn't try to speak to this issue, it does. And I will talk more about why science cannot speak to this issue next week when I talk about the Big Bang. But scientists, I think, are somewhat myopic, but they do try to answer this question. And one of the most famous people to try to answer this question is Stephen Hawking. And I think most of you know who he is. He really was he had a really remarkable life. He's a physicist, very influential, very successful in terms of his scientific work. And Stephen Hawking, near the end of his life, ascribed to something called M-theory, which is a form of string theory. And what he decided is that because there are quantum fields in gravity, matter can pop in and out of existence, and therefore you don't need God. And here's what he said. Because there is a law such as gravity, the universe can and will create itself from nothing. It is not necessary to invoke God to light the blue touch paper and set the universe going. Now, other than the fact I have no idea what blue touch paper is, I think you get the sense of that. But what he ignores is the fact that a quantum field and gravity and the other forces which he presupposes exist had to come from somewhere. That's not nothing. And this is a very common issue when scientists begin to look at the reality in which we live and try to come up with answers for it. So that's really the first question. Why is there something rather than nothing? And now I want to talk about some of the fundamental aspects about reality that we have become aware of, and largely through science. The first is that reality is intelligible. And that means we can understand it at some level, we can make some sense of it. And the way that science does this is really through the language of mathematics. And certainly in physics, if you can't do the math, if you can't represent it with an equation, it can't be right. That is the way that physics looks at the world and tries to make sense of it. And there is an interesting question among mathematicians and philosophers and physicists, is whether math is discovered or created. And when you say it's discovered, what they mean is that the mathematical relationships actually exist in the universe. And we are simply discovering what those relationships are and figuring out how to use those. The other theory is that math is created by man as a way to try to make sense of reality. And in that sense, it's an approximation of what we see, but it doesn't actually represent what's going on. Now, this is not a resolvable question. It's an interesting question, but it is an ongoing discussion in the mathematics and physics world. So reality is intelligible. Then the next thing I want to talk about are the four forces. And there are four things I want to talk about there. There are four forces that underlie everything in the universe. They are the only forces we're aware of. And they are the strong nuclear force, the weak nuclear force, electromagnetism, which includes light, and gravity. All the gravity have been incorporated into something called a standard model. They can't figure out how to put gravity in there to make it all work together. But there are four forces, and there are just four of them that we're aware of at this point. Also, the four forces have very specific values, and science has not been able to discern a reason that those four forces have those particular values. However, they also recognize that if those four forces did not have the particular values that they have, the universe could not exist in the way it does now. It would not exist, and we would not be sitting here. Again, no particular reason that they can determine for that. And the fourth point I want to make about the four forces is that they appear to be and are believed to be immutable. That means they don't change over time. So as far as we are aware, when the four forces first came out of the Big Bang, they had the same value, and the whole universe is constructed on those values. So those are the four forces. Now, the next thing I want to talk about is we live in 4 dimensions. There's 3 spatial dimensions and time. There's not a lot to say about the 3 spatial dimensions. It's pretty straightforward, except to say that if you are an adherent of string theory, they may be dealing with up to 26 different dimensions. I don't really understand it, don't know how it works, but that's what the math tells them may need to be the case. But I want to talk a little bit about time. And the question I want to ask you is, what is time? I mean, it's a much more challenging and difficult question than you might imagine. Time, and so this is the definition of time, or a definition of time: the measured or measurable period during which an action, process, or condition exists or continues, a non-spatial continuum that is measured in terms of events which succeed one another from past through present to the future. And I've highlighted the word measurements here because that's the only way that we have to really describe it. It's how we measure it. But this doesn't really tell you what time is in its essence. Conceptually, what is time? It really is a very challenging question. But I'll tell you some of the things we know about time. Number one, time, we believe, began at the Big Bang and did not exist before then. Second, we use time to measure other quantities like velocity. They're measured by time. We can measure time exceedingly accurately. The most accurate clocks right now are based on the frequency of cesium atoms, and they're extremely accurate. Time appears to be a continuum, and one of the reasons this is important is that when we talk about quantum mechanics, one of the things we found about the world of the very small is that everything is quantized. They come in little packets. They're not a continuum. Light is not a continuum. It comes in little packets of energy, little tiny packets of energy, but packets nonetheless. The arrow of time is unidirectional. It goes from the past to the present to the future, and that never changes. Now, we are stuck in the present. We can't move forward. We can't move back. But we can see into the past. We can see into the past through our memories. We can see into the past through the fossil record. We can see into the past now through the genomes that we've decoded, because there is a history there of how that came to be. And most importantly for an astrophysicist is we can see into the past by looking very deep into the universe. When you are looking at a galaxy that's 1 million light years away, you're looking 1 million years into the past. So we can actually see into the past. And one of the other things that I think is interesting is that everything that we know, everything that we perceive has actually happened in the past. You're looking at me and you hear my voice, but it takes a little bit of time for my image to hit your retina, for that to be processed by your mind. By the time you have the image of me, that's actually in the past. With all of this, we're stuck in the future, we can see the past, but we can't see the future at all.
Stuck in the present. Stuck in the present.
We are stuck in the present. But if we can't see the future, we can't move into the future at all. Not even a nanosecond. And finally, time is relative. I'm going to talk more about general relativity in a minute, but time is relative. Time is actually different for each one of us as we live our lives. It's imperceptible, but it's real. This is one of the things that came out of general relativity. Time slows down the faster your velocity. Time speeds up the less gravitational pull there is. So time is actually slower time is actually a little bit faster on the second floor of your house than the first floor. And they have, one of the experiments that was done when Einstein came up with this theory is they took two clocks that were perfectly synchronized and extremely accurate. I think this was in Vermont for some reason. But they took one and put it on a mountain for a few days, and they brought it down, and the one that was on the mountain was actually a little bit faster than the one that had been left at sea level. Time is actually different for different people in different circumstances. Also, the only reason GPS works is that we make an adjustment for the change in time. If we didn't make that adjustment, it would be off about 6 miles a day. One other concept, this was a hard one to get your head around, there is no concept of now in the universe. You cannot pick a time right now and say, I want to know everything that happens now in the universe. There is no concept of simultaneity because time is relative for everyone. So time is actually more of a challenge than you might have realized. The last thing I wanted to talk about in terms of the fundamental structure of reality is the speed of light. And one of the things Maxwell's equations back in the 19th century came up with, and this is one of the most important things that Einstein looked at, is the speed of light is absolute for everybody under all circumstances. And nothing can move faster than the speed of light. Speed of light's roughly 186,000 miles per second. It's quite quick. But we have no explanation for what that is. So these are sort of the fundamental building blocks of reality that we have learned through science. But science really has no explanation for them. And what has happened is that these have become, in essence, I believe, metaphysical assumptions on which all of science is based. Yes, they were originally observed and they've been tested and verified. But I can tell you when scientists are looking at a galaxy 10 billion light years away, they're not asking if the four forces have different values. They're not asking if we can figure that out with math. They're not asking if the speed of light has a different speed 10 billion years ago. They are assuming all those things are true when they're trying to determine its composition and how it behaves. Now, are those reasonable assumptions? Oh, I think they are. Are they right? I don't know. But if any of these proves not to be the case, that would change an awful lot about what we know about reality and about science. So now what I want to do is I want to go through some of the history of how we have learned about how the universe works. And I'm going to start with philosophy, which is really the most ancient form of analysis that we had. And in the ancient world, there were basically three types of philosophy, three categories. One is metaphysical philosophy, which deals with existence, God, logic, Platonic forms. Another is moral philosophy, which is how to live a good life, goodness, right and wrong, justice, virtue, beauty. And the third was natural philosophy, which is really trying to understand the natural world. The earliest records go back to 6th century BC in Greece, but the most famous of these philosophers and the most influential is Aristotle. He was born in 387 BC. He was part of Plato's Academy and is generally considered the father of Western philosophy. He was really the first philosopher, the natural philosopher, to take a very systematic approach and make very, very careful observations about the world. And he looked at cosmology, biology, physics, psychology, memory. He was very interested in memory. He dissected animals to try to classify them, and he made very careful observations about the heavens and about the movement of bodies and how all that worked. And his observations were very accurate. He could predict the movement of some bodies, but his theories were just wrong. He believed that the Earth was a center and everything moved around it. He believed that bodies had their own natural motions and didn't affect each other in the way that gravity actually does. And he believed that the universe was steady state, that it was eternal and unchanging, and we know that's not the case now. We'll talk more about that next week as well. But his observations and his beliefs about this really were highly influential for about 1,800 years until the time of Copernicus. And one of the other things that was different about him and modern science is that his observations were largely qualitative in nature. They were not quantitative. He was not using mathematics to build relationships between things. So it was mainly qualitative. That began to change in the 16th and 17th century with Copernicus, Kepler, Galileo. They began to marry both their careful observations and produce mathematical equations to try to understand it. But modern science really started with Isaac Newton in 1640, who was born in 1642. And his book, which is probably the most famous science book ever published, was Principia Mathematica in 1687. And he laid out the foundations of classical mechanics, the three laws of motion and the law of universal gravitation. These laws are still used today. They remain accurate. They were incomplete in that they didn't take into account some of the things that quantum mechanics and general relativity do, but they were still very good science. He invented calculus to be able to figure out how these things worked. And there were really two keys to what he did. One was the use of mathematics to develop these laws, including the development of calculus. But what he did that was different from what other people had done is he really developed these laws of universal application that applied not only on Earth, but in the heavens as well. And so his was really the beginning of science. Now I'm going to skip to Albert Einstein, who was obviously a very influential figure. And he was really monumental intelligence, and the way that he developed his ideas and developed his theories was really through thought experiments. And I'm not going to go into the details of the thought experiments, but he would present a problem in a very simple thought experiment, and then try to figure out how that worked, how to do the math, and he came up with some really remarkable insights. One of the things that I have referred to that he knew based on Maxwell's equations is that the speed of light appeared to be absolute for everyone. There is a concept of relativity for different observers, and I'm going to give you a very simple explanation of that. And if I'm riding on a train and we're going 100 miles an hour and I throw a ball from one end of the train to the other, for me the ball is going 50 miles an hour, if I could throw it that fast. But for an observer on a platform watching this, the train's going 100, the ball's going 50, that's going 150 miles an hour. The ball's going 150 miles an hour. So that's the concept of relativity in different observers. And what Einstein, his great insight was, if the speed of light is absolute and always the same for all observers, no matter what the circumstance, then time and space have to be relative. Time and space have to be malleable. Time and space have to change. And that was really his great insight. And so there were a number of conclusions that he drew from this. One is that time and space are really a single continuum called space-time. They are woven together in one entity called space-time. He also, from this, figured out that mass and energy are equivalents. Mass can turn to energy and energy can turn to mass. And he developed his famous formula for that, which is energy equals mass times the speed of light squared, E equals mc squared. If you think about that, the speed of light is 186,000 miles per second, and you square that, that's a really big number. And just to give you an example, a paperclip has the same amount of energy wrapped up in its mass as the bomb on Hiroshima. That's how much energy is stored up in matter. Now this was special relativity. It does not involve acceleration or gravity. And so that paper was published in 1905, and he spent the next 10 years trying to figure out how to put gravitation and acceleration into his theory. And finally, in 1915, he published a second paper in which he proposed general relativity, and where he incorporated gravity, and that is when he figured out that it was actually a curvature of space-time, not a force, which is what everybody had thought before. It's actually a curvature of space-time that is gravity. And many of you may have seen this before, but I'll try to explain it. This is the way most people try to explain how space-time is curved. In this example, and I hope you can see it, but in this example, what you have is basically a sort of like a rubber sheet with a grid on it, and then you drop balls here, say planets, on it, and you can see how the rubber sheet is actually impacted by that. The rubber sheet is curved in a certain way. And so if you had a planet going around, a moon going around a planet here, the planet is actually moving in its world in a straight line. But because space is curved, it's actually going around the planet here. And so that's what you see. And the larger the planet, the more curvature of space-time. But obviously this is 2 dimensions. Space-time is 3 dimensions. We have a hard time getting our brain around that. But that's essentially what happens. And so when you see light, and this is one of the experiments I did to try to prove this, and all of this has been proven experimentally. One of the things they tried to do is they watched light bend around a planet and recognized that it was actually bending through space, and space is actually curved. So that's Einstein and general relativity. And that's really the easy part. So now we get to quantum mechanics. And quantum mechanics is the fact that we have figured a lot of this stuff out is just enormously impressive, but it is really hard to get your head around. General relativity applies to the very large and the very fast. Quantum mechanics deals with the world of the very small. It was developed by many people over many years: Niels Bohr, Paul Dirac, Erwin Schrödinger, Werner Heisenberg, Max Born. All of them made contributions. There was no one like Einstein who had this aha moment as he did over 25 years or so. And all of this with quantum mechanics has been experimentally verified. And I'm going to give you a few of the elements of this to try to give you a sense of what it's all about. First, as implied by the name, and I mentioned this, at the very small level, everything comes in little packets. There's no continuum, and so you have little packets of energy and particles all come in little packets. Hence the name quantum. Also, everything has a dual nature. All particles, light, everything at that level acts sometimes like a particle and sometimes like a wave. So if you think about light, if you have a photovoltaic cell, that is when light is acting like a particle. When the photons hit electrons, it creates electric power. But when you push light through a prism and you see the colors separate, that's when light is acting like a wave. Sometimes these things act like particles, sometimes like waves. Don't really understand it, but it's all been proven experimentally. The most difficult and challenging part to understand, however, I think, is the fact that everything at the quantum world operates on the level of probability. Now, when I was growing up in school and we looked at an example of an atom, you had a ball that was a nucleus that held neutrons and protons, and then you had electrons going around in orbits like, little planets around the sun. But that's not the way this world works. All we can know about the position or location of a particle, an electron or anything else, is its probability that it'll be in one place or another place. And essentially what we're doing is we're calculating the probability that a particle will be in one location versus any other location in the universe. And if you actually did the experiment and there was a 64% probability that this particle would be in one location, and you did it 100 times, 64 times it would probably be in that location. That's the only way that we can learn about it. And then there's the measurement problem. we cannot know the velocity and the location of a particle at the same time. You can only do one or the other. On top of that, when you measure something, it affects it. So when a human scientist measures something at the subatomic level, it impacts that particle in certain ways. It actually has an effect on it. And now I'll come to the most challenging thing and the most interesting thing in many respects to me is the concept of entanglement. And in entanglement, if you have two particles that interact in a certain way and then they're separated, a measurement of one will simultaneously yield the same result in the other particle no matter where it is in the universe. Now, this would seem to violate the speed of light, but the theory is this is a concept of non-locality, and somehow these particles are communicating or something so that it happens to them simultaneously no matter where they are. And this has all been proven experimentally, and in fact entanglement is one of the things that is being used now to build quantum computers, which would be able to operate at millions times the speed of our current computers, which are based on silicon chips. So quantum mechanics is tough. I mean, it's very difficult to get your head around. There is no consensus on how quantum mechanics fits with general relativity. This is part of the problem that we're facing. And no one understands what the world at the very small looks like, given the nature of probability. From my perspective, this is really where we begin to come up against the limitations of human imagination and human intellect. I think we have reached that point with quantum mechanics. Now, one of the things that's, and I talked last week about the problems with interpretation. One of the things that, when scientists are looking at data, if the data is the sun rises in the east every morning, that doesn't require a lot of interpretation. When you get down to dealing with quantum mechanics, I talked about the Higgs boson last time, you're dealing with enormous amounts of data that require a certain level of interpretation. And one of the most interesting things about this to me is that Albert Einstein, the quantum mechanics was being developed in the early part of the 20th century. Einstein was very much a part of this. In fact, Einstein was one of the people who developed the concept of duality, that light, in his case, he was focused primarily on light, acts both as a particle and a wave. And he was very much involved in the discussions. But you may have heard his famous phrase, God does not play dice with the universe. And he never could accept, until he died, the probabilistic nature of quantum mechanics because of his perception of how the world should work. And so I think this is a very good example that the interpretation that scientists go through really does matter, and it is impacted by who we are and how we think about the world. So now we have general relativity, we have Newtonian mechanics, and quantum mechanics, and there is an effort that is ongoing and continuing to try to pull all of this information together into a theory of everything. And this is basically trying to put quantum mechanics and general relativity together. General relativity is based primarily on gravity, and that's the one piece they have not been able to put together. The main theory along these lines is called string theory. It is based on a concept that you have these little tiny vibrating strings that make up everything, including gravity. It requires at least 10, but perhaps as many as 26 different dimensions. And one result of the string theory that comes out of that is the concept of a multiverse, and I'm sure you've heard about this, but the concept of a multiverse is that we live in one universe, but there are potentially an infinite number of universes, each with their own set of physical laws, et cetera, et cetera. The problem with string theory is there's really no way to test it experimentally. And so what this becomes, and I'll talk more about this next week, but what this becomes is really a form of scientific speculation or mathematical philosophy, whatever you want to call it. But you can't observe it because we can't even see our entire universe, much less another one, and you can't test it experimentally. So there's a question there about whether it is science at all. The other major theory, which is less well known, is loop quantum gravity, and this is really an effort to quantize gravity so that it can fit in with quantum mechanics. So there you have it. All you wanted to know about physics, but we're afraid to ask. So let's look at some of the takeaways from today's session. Science has determined a number of things that form the foundation of all scientific knowledge, which it accepts as true, but that it is incapable of explaining. The intelligibility of reality through mathematics, the fine-tuning of the four forces, the absolute nature of the speed of light. Something other than science is required to explain these things. The power of science is its ability to discover through observation and experimentation what reality is. The nature of reality is unexpected and mysterious. You can't make this stuff up. Scientific knowledge is incomplete and likely will always be so. We are peeling the onion one layer at a time, and we don't know how big the onion is. We cannot understand what we have learned. With quantum mechanics, we may have reached the limits of human understanding. We are the chimpanzee. So there you have it. Physics for poets, physics in one easy lesson. We do have wine and snacks over here, which we encourage you to enjoy with us. I encourage you to stick around and have some conversation. Any questions about any of this? Yes, ma'am.
What is a particle?
A particle? A particle is the generic term used to describe protons, neutrons, electrons, quarks, gluons, all of the little things that make up matter. Yes?
I have two questions. My first question is inspired by your quote, the arrow of time is unidirectional.
Yes.
When I heard that, it kind of confused me a little bit, because when I think about time or existence, and maybe those are two different things, but when I think about that, I think about it as being infinite in both directions, as the arrow pointing in both directions. So why is time unidirectional?
Time, as we understand it, and as we are trapped in it, if you will, is unidirectional. It only moves from the past to the future. In science, you can do mathematical equations that theoretically could be true, though we've never observed it, where time can go in the other direction. But as far as we're aware, time is always moving in one single direction.
And then my second question is, I was super intrigued by when you were talking about the greater your velocity, the slower time progresses, and how time is relative, and how time moves at different speeds on the first floor of your house, or second floor of your house. What would you recommend as just basic search terms if I wanted to look into that more, because it's really interesting?
Well, I think just if you look at relativity and time, there's a ton of stuff out there. And there's actually a lot of stuff on the internet that's quite good that focuses on very narrow issues like that. So I think you'll be able to find it pretty easily. Yes, sir.
My question is, this is a particle question, but if, we've gotten pretty good at figuring out subcellular function anatomy is at a very small level. We need an intracellular function. And it seems to be well organized. And yet you're saying that the particles are so much smaller than that each one of these smaller things in a cell is made of those particles,
yes,
which we don't even know where they're going 60% of the time. So, I'm glad. Why is my body this?
That's a very good question. The particles that I'm talking about, which are atomic and subatomic particles, are dramatically smaller than anything in a cell. Any of the elements of a cell. Does that answer your question?
Well, I Not really, because it kind of would like to know that they had some direction or knowledge or something, or they had some purpose, or rather than just it's random. Like,
Well, we're going to talk more about that concept of random versus purpose, and probably in the 5th session. But I mean, there are laws that govern the behavior of particles and biological laws that govern biology. This does get to the question of, which I'll address in the 4th one, on life, the distinction between reductionism, which is the belief that everything is reduced to particles, and if you had all the information about how particles vibrated, you could figure out who you're going to marry. That's sort of the concept of reductionism. And then there's the concept of emergence, which when you get to certain levels, you cannot predict it through particles. They have their own laws that apply to them. And so there are physical laws that make up particles, and then you have biological laws that make up biology. I don't know if that helps you or not.
Do the forces, and perhaps light also is sort of not exactly a force, but it's another independent, do they constrain the probability of the information, I guess, on a given particle?
Do they restrain?
So do they constrain you've got these 4 forces. Does that increase the probability that a particle does A, B, C, or an infinite range of things?
No, I mean, the 4 forces are what they are. And the particles and their behavior is dependent on those 4 forces.
Right.
So there's no sort of constraint. They are what they are, and that's particles are dependent on those 4 forces and how they operate.
Would you name the 4 forces? I learned in school that force was equal to mass times acceleration, but that's a force. What are the 4 forces?
The 4 forces are the strong nuclear force, the weak nuclear force.
I'm sorry, speak.
I'm sorry, the strong nuclear force, the weak nuclear force, electromagnetism, which includes light, and gravity.
Thank you.
Yes. Yes, sir.
You talk about we see the past and the present. You say we can't see the future. Now, we know the sun's going to disappear in 4 billion years. I can't give you the date and time. I can say it's gone.
We can make predictions, but we cannot observe the future. We can actually observe the past when we look at a galaxy a million light years away. But we cannot actually observe in real time the future. We can predict it, but that's very different from observation. We're going to talk a lot more about that next week. Yes, ma'am.
The only thing I understood enough about to ask a question was, you said there was the same amount of energy in a paperclip as there was in the bomb dropped on Hiroshima, and I'm having a hard time wrapping my head around that.
Well, the point there is that when you convert mass to energy, a very small amount of mass creates an enormous amount of energy. So when they dropped the bomb and you had this nuclear reaction, it used up a paperclip's worth of mass to create the bomb at Hiroshima. That's effectively what happened. They didn't actually use paperclips.
I think if you could create a, what's the word, chain reaction in the paperclip or a piece of wood, you can create a nuclear bomb.
Yes.
You just can't do that.
Ted?
This is an easy one. Nomenclature. Is the term unified field theory obsolete now? Can we replace it with some of these other things?
No, I mean, unified field theory is still a term of art that is used in certain circumstances, and but no, this is a different way to look at it, but that's very much, quantum field theory, unified field theory are all very much the same thing. Anybody else? Yes, ma'am.
Oh, yeah. I really like the title that you have for Is There Room for God in Our Understanding of Reality? And so I was wondering, after we've learned for a few weeks these specifics from the scientific point of view, will we also be talking about the theological part of things?
That's Father Dunbar's. I'm just taking notes. Yeah, just so you understand, my focus here is really to show what science is capable of explaining to us, which is a huge amount of information. I mean, it's remarkable what we achieve, but there are certain limitations to it. And so hopefully for me, that creates space for God. And I am going to talk a little bit about that, particularly in the last session, and specifically about a guy named Jon Polkinghorne, who is a theoretical physicist and then became an Anglican priest and has written extensively about the connection between science and faith. So I'll touch a little bit on that, but I'll leave most of that to Father Dunbar. Anyone else? Thank you all for coming. I hope